Good day everyone, my name is Kate Tobilid of BSECE 3A, and today I'm going to present to you my performance task number 10 in ECE 23. And my design topic is all about Sonnet or Synchronous Optical Network. Now connecting all the things we studied in ECE 23 together, when data is transmitted over a communications medium, a number of things must be provided on the link. That includes framing of the data, error checking, and the ability to manage the link. Although there are a lot of similarities between Sonnet and SDH, there are some significant differences, especially in terminology. In an attempt to avoid totally confusing the reader, I have focused primarily on Sonnet and Sonnet terminology. This does not mean that I think Sonnet is more important than SDH. It is just easier to explain things from a Sonnet point of view because Sonnet is a subset of SDH. But both Sonnet and SDH are standards which provided a more efficient way of transmitting the digital data by using optical methods. Now once you understand Sonnet, it is easier to understand SDH. Before I jump into Sonnet SDH, let me cover a bit of telephone communications history to review how we got to optical communications and the problems the designers and engineers were trying to solve. Now for many great years, telephone calls were handled in the analog domain. Long-distance calls were routed over twisted pairs coaxial cable or analog microwave between major switching offices. Any viewers old enough to remember these long-distance calls will recall the amount of noise and crosstalks in these calls. Hence, you always know when someone was calling a long distance. Now in 1962, AT&T began installing the S1T carrier services between long-distance switching centers. Basically, these were channel banks, which took 24 analog telephone circuits, converted them to digital, and then transmitted them over copper to the other switching center where they were converted back to analog. So this actually worked very well. It reduced the number of copper circuits required between switching centers and improved the quality of the telephone calls. Now as the volume of long distance grew, the number of TKR circuits required between switching centers increased. Additionally, the S1C and the S2 signals began to be used to increase the capacity of a circuit. Now in the late 1970s, optical communications became feasible, allowing higher speed communications, which means that one circuit could carry many more telephone calls. Now, for example, one of the first commercial fiber circuits was installed in Chicago in 1977 and operated at 45 Mbps, so that is DS3 rate. Now, in those days, the telephone companies looked at optical communications as simply a replacement for the older wire or microwave communications they had been using for years. But then they encountered a practical problem. Vendors of optical communications equipment had used their own framing techniques on the optical fiber. Now, once you selected a vendor, you were stuck with that vendor for all of the equipment in that optical network. Thus was born the concept of a standards in optical communication. Now, introduction. Information is sent over an optical fiber by turning the light off and on in the fiber. For example, suppose that the presence of light indicates a 1, while the absence of light indicates a 0. Just knowing this much, we can send and receive bits across an optical link. But how do we extract the information from those bits? This is where Sonnet SDH comes in. So Sonnet SDH defines the low-level framing protocol used in these optical links. By framing, we mean a block of bits or octets which have a structure and which utilizes some techniques which allows us to find the boundaries of that frame structure. Part of the block may be devoted to overhead for the network provider to use to manage the network. Other parts will be dedicated to carrying payload or information we want to communicate. So service providers' networks are complex and consist mostly of high-bandwidth fiber optic media using either Sonnet or synchronous optical networking, which is the ANSI standards in the US and Canada, or synchronous digital hierarchy, which is everywhere else and is an ITU standard. So they're both pretty much interchangeable. And you can see the different signals hierarchies for both. They're just labeled either as OC1 or STM0, OC3 or STM1. So glancing through this table reveals some important points. First, the lowest level in this hierarchy has a data rate of 51.840 Mbps, which is greater than of the DS3 service, which I mentioned a while ago, which was 44.736 Mbps. In fact, the STS1 is designed to accommodate data rates equivalent to those of the DS3 rates. The difference in capacity is provided to handle the overhead needs of the optical system. Second, the STS3 rate is exactly 3 times the STS1 rate, and the STS9 rate is exactly 1/2 of the STS18 rate. So these relationships mean that 18 STS1 channels can be multiplexed into 1 STS18, and 6 STS3 channels can be multiplexed into 1 STS18, and so on. Now, before we jump into the Sonnet SDH frame, there are some other terminologies that we need to talk about in Sonnet devices. Alright. So the end-to-end connection through a Sonnet SDH network is always called the path. So this is the end-to-end portion of the network between the two STS multiplexers. Next, the connection between major nodes, such as between add-drop multiplexers, is called the line. So it is the portion of the network between two multiplexers, STS multiplexers, two add-drop multiplexers, and two add-drop multiplexers, or two STS multiplexers. Next, the link between an odd-drop multiplexer and a regenerator, or between two regenerators, is called a section. So a section is the optical link connecting two neighbor devices. So that's multiplexer to multiplexer, multiplexer to regenerator, or regenerator to regenerator. Remember that back in the mid-80s, the only kind of signal amplification available was electronic regeneration. So optical amplifiers had not yet appeared. Now let's discuss this simple link using Sonnet devices. You see, Sonnet transmission relies on 3 basic devices. That is the STS multiplexer, demultiplexer, regenerators, and add-drop multiplexers and terminals. So STS multiplexer, demultiplexer marks the beginning points and the end points of a Sonnet link. They provide the interface between an electrical tributary network and the optical network. An STS multiplexer multiplexes signals from multiple electrical sources and creates the corresponding OC signal. An STS demultiplexer demultiplexes an optical OC signal into corresponding electric signals. And after the STS mux and demux, we have the regenerator. So a regenerator is a repeater that takes a received optical signal, demodulates it into a corresponding electric signal, which is the STS, regenerates the electrical signal, and finally modulates the electrical signal into its correspondent OCN signal. A Sonnet regenerator replaces some of the existing overhead information with the new information. Now, next to the regenerators, we have the add-drop multiplexers, which add the STS signals coming from different sources into a given path, or can remove a desired signal from a path and redirect it without demultiplexing the entire signal. Instead of relying on timing and bit positions, add-drop multiplexers use header information such as addresses and pointers to identify the individual streams. Now, in this simple configuration, a number of incoming electronic signals are fed into the STS multiplexer, where they are combined into a single optical signal. The optical signal is transmitted to a regenerator, where it is recreated without the noise it has picked up in the transit. The regenerated signal from the number of sources are then fed into the add-drop multiplexer. The add-drop multiplexer reorganizes these signals, if necessary, and sends them out as directed by information in the data frames. These remultiplexed signals are sent to another regenerator, and from there, the receiving STS demultiplexer, where they are returned to a format usable by the receiving links. And then the terminals is a device that uses the service of a Sonnet network. For example, in the internet, a terminal can be a router that needs to send packets to another router at the other side of a Sonnet network. Alright, we're done with Sonnet devices. Let's jump over to Sonnet layers. Now, Sonnet standard includes four functional layers. We have the photonic layer, the section, the line, and the path. They all correspond to both the physical and the data link layers, if you can recall our module 1. So path layer is responsible for the movement of a signal from its optical source to its optical destination. At the optical source, the signal is changed from an electronic form into an optical form, multiplexed with other signals and encapsulated in a frame. At the optical destination, the received frame is demultiplexed and the individual optical signals are changed back into their electronic forms. So path layer overhead is added in this layer, and STS multiplexers provide the path layer function. Next, we have the line layer, which is responsible for the movement of a signal across a physical line. So the overhead in the line layer is added to the frame at this layer. STS multiplexer and Drop Multiplexer provides line layer function. Next is the section layer, which is responsible for the movement of a signal across a physical section, where it handles framing, scrambling, and error control. The overhead of the section layer is added to the frame at this layer. You see, this 3 is associated in the data link layer. And I suppose you already know what is the operations inside the data link layer in our module 1. Next, we have the photonic layer, which resides in the physical layer. So it includes physical specification for the optical fiber channel, the sensitivity of the receiver, multiplexing function, and so on. So Sonnet uses energy coding with the presence of light representing a 1 and the absence of light representing a 0. Both the Sonnet devices and Sonnet layers have a relationship with each other. Let's combine for better understanding. So this figure right here shows the relationship between the devices used in Sonnet transmission and the four layers of the standard. As you can see, an STS multiplexer is a 4-layer device, and a drop multiplexer is a 3-layer device, and a regenerator is a 2-layer device. Remember I mentioned earlier that the Sonnet designers were interested in carrying their legacy Plesiosaurus traffic. Because of this, they tied everything to the existing voice traffic. In the digital telephone network, voice is digitalized according to ITU specification G711. That is the granularity of the voice samples in 1 octet, and samples are taking 8,000 times per second, or every 125 microseconds. How the basic sonic frame is shown here. So it is a figure of 9 rows and 90 octets. It is transmitted from left to right and top to bottom. That is, the octet in the upper left corner is transmitted first, followed by the second octet, first row, etc. When we get to octet 90, we come back and start with the first octet of the second row. The first 3 columns of a sonnet frame are called the transport overhead, and you see that label. The 87 columns following the TO is the SPE, or the synchronous payload envelope. Within the SPE, there is another column of overhead, called the payload overhead, whose location varies because of timing differences between the networks, but we won't explore this aspect right now. So this leaves us 86 columns by 9 rows for usable payload in this basic frame. Now, one of the interesting points about Sonnet is that each STS signal is transmitted at a fixed rate of 1,000 frames per second. This is the rate at which voice is digitalized. You can read this at chapter 4 in the book entitled Data Communications and Networking by Beros Furuzan. For each frame, the bytes are transmitted from the left to top to bottom. For each byte, the bits are transmitted from the most significant to the least significant, hence it's from left to right. Now the figure on the right shows the order of the frame and byte transmission. If we sample a voice signal and use 8 bits for each sample, we can say that each byte in a Sonnet frame can carry information from a digitalized voice channel. In other words, an STS1 signal can carry 774 voice channels simultaneously. So that's 810 minus required bytes for each overhead. Now let's clear some basic things up by explaining the data rates. So find the data rate of an STS1 signal. So STS1, like other STS signals, sends 1,000 frames per second, and each STS1 frame is made of 9 by 1 by 90 bytes. So each byte is made of 8 bits, so the data rate will be given by 51.840 Mbps. So next, Find the data rate of an STS3 signal. So STS3, like other STS signals, sends 8,000 frames per second. Each STS3 frame is made of 9 by 3 times 90 bytes, 9 by 3 times 90 bytes, and each byte is made of 8 bits. So the data rate is given by solving this, so we will have 155.52 Mbps. Note that in Sonnet, there is an exact relationship between the data rates of different STS signals. We could have found the data rate of STS3 by using the data rate of STS1, so just multiply the latter by 3. Next, find the data rate of an STS9 signal, so same principles. We are going to have 466.560 Mbps. Now, what if we are asked, find the user of an STS9 signal? Now, the user part in an STS9 frame is made up of 9 rows and 86 columns. So we will have 445.824 Mbps. Now, the user part in an STS frame is made of 9 rows and 86 columns. So we have each STS and frame carries as given by n times 9 times 8 times 86 bytes of bytes. And Sonnet sends 8,000 frames in each seconds. Now, what is the duration of an STS1 frame, STS3 frame, or any other STSN frame? So in Sonnet, 8,000 frames are sent per second. This means that the duration of an STS1 or STS3 or other any STS frame is the same and equal to 1 over 8,000 seconds or 125 microseconds. So in Sonnet, the duration of any frame is 125 microseconds. Now, back in the STS1 frame format we said before, a sonnet frame is a matrix of 9 rows and 90 bytes or octets each, for a total of 810 bytes. The first 3 columns of the frame are used for the section and line overhead. The upper 3 rows of the first 3 columns are used for a section overhead. The lower 6 are the line overhead. The rest of the frame is called the synchronous payload envelope, and as you can remember, it was the color green. It contains the user data and path overhead needed at the user data level. So here in these 2 slides, you can see each octet together with their function, but we won't discuss this aspect in every octet for now, as it is a very long discussion. Next, I'll just show you the summary of each octet function as an overview. And let's go over to the Sonnet Networks. Now, using Sonnet equipment, we can create a Sonnet network that can be used as a high-speed backbone carrying loads from other networks, such as ITM. We can roughly divide Sonnet networks into 3 categories. We have linear, the mesh networks. Since I already provided the explanation, you can just read it. I'll just summarize anyway. I will provide a copy of this in the description description box. Now, in linear Sonnet networks, it can either be a point-to-point network or a multi-point. In linear Sonnet networks, to create protection against failure in linear networks, Sonnet defines automatic protection switching where the idea is to provide redundancy. And there are 3 schemes in common for protection in linear channels. These are 1+1 APS, 1-to-1 APS, and 1-to-many APS. Back into the taxonomy of Sonnet networks, we have ring networks. And under that, we have the UPSR and BLSR, or the unidirectional path switching ring and the bidirectional line switching ring. And here's the figure showing the combination of both rings. And the last in the taxonomy of Sonnet networks, we have mesh networks. And here's a figure showing the mesh Sonnet network and the structure of a switch. And for a summary, Synchronous Optical Network, or Sonnet, is a standard developed by ANSI for fiber optic networks. Synchronous Digital Hierarchy, or SDH, is a similar standard developed by ITUT. Sonnet has defined a hierarchy of signals called Synchronous Transport Signals, or STS, and SDH has defined a similar hierarchy of signals called the Synchronous Transfer Modules. Now, excuse me. An OC signal is the optical modulation of an STSN signal. Sonnet defines 4 layers. Remember, it was the path, line, section, and photonic. Sonnet is a synchronous TDM system in which all are locked to a master clock. Sonnet system can use the following equipment. We have the SDS multiplexers, STSD multiplexers, regenerators, and drop multiplexers and the terminals. So Sonnet sends 1,000 frames per second, and each frame lasts for 125 microseconds. An STS1 frame is made of 9 rows and 90 columns. An STSN frame is made of 9 rows and n times 90 columns. An STS can be multiplexed to get a new STS with a higher data rate. And Sonnet Networks topologies can be linear, ring, or mesh. A linear Sonnet network can either be a point-to-point or multi-point. A ring Sonnet network can be either a unidirectional or bidirectional. So that is all for today. I hope you got the overview about Sonnet Networks. Good luck and good health.